Yep, you can get started. Go ahead. Thank you.
Welcome to one and all. And today I'm going to present on the topic integration of blast-resistant genes into a light line cultivar KMP149 through marker-assisted selection. Blast is the most destructive and the widespread disease, and it is listed as one of the #1 of the 10 most important fungal pathogen. As you can see in the diagram, there are different types of blast disease, that is leaf, nodal, colar, and the neck blast. Initially, it is gray at the center with the dark brown border, and eventually, finally, with the favorable environment, it coalesces and thus leading to death of the whole plant. And the yield loss due to this blast disease is normally 75% and more in the disease conducive condition. And as we all know that most of the world's population calories is dependent on the rice, and thus yield loss due to this blast disease can be a major threat to the food security at the global level. So for this, we have selected two donors. That is, we have selected KMP149 as the female parent because initially it was sent for the varietal trial because of its medium duration, semi-tall, fine grain and good cooking qualities, but it was susceptible to blast. So in order to circumvent that, we have selected IC2 as a male parent harboring PI9 and PI54 gene. And the breeding scheme which I'm following is initially I'll be crossing these two parents to get FN, and the genes will be checked out, and with the subsequent backcross I'll be going through BC2F2 where I'll screen for the blast resistance in the uniform blast nursery. And we have selected two markers for the 4-1 selection, that is NMSM PI9 for PI9 gene and PI54 for the PI54 gene, which are located in the chromosome number 6 and 11. And you can see in the figure that KMP149 is susceptible at 250 base pair and 350 base pair for PI9 and PI54 gene, and IC10 is resistant at 168 and 216 base pair for these two genes. So we have crossed these two parents in order to get the FNs, and thus 4-1 selection has been carried out here. And with the subsequent back crosses in BC1F1 and BC2F1, we have again checked for the presence of genes, and the genes and the population having the heterozygous, that is having both the female susceptible and the male resistant bands have been selected, and the best plants have been carried forward. We have also selected the polymorphic markers, as we have, you can see in the diagram. We have used more than 300 markers, and in that, we have got 78 markers to be polymorphic, and they're flanking all over the regions of 12 chromosomes of rice. So using this polymorphic markers, we have carried out background selection using the formula which is given here. And the number of, N is the total number of polymorphic markers, X is the marker showing homozygosity with the female parent, and Y is the marker showing heterozygosity. So using this formula, we have calculated the percentage recovery, that is recurrent parent genome recovery. And in BC1F1, we have got a recovery percentage of 78%. And thus, this best plant selected here is been backcrossed to produce the BC2F1. And here also we have done the identification of genes, blast resistant gene, and we have calculated the recovery percentage, and it is 89%, thus indicating that backcrossing will ultimately increase the recovery percentage of the female. And presently, I'm in BC2F2 generation, where I will be selecting the best plant on the basis of foreground and the background selection. And at last, the best plant here selected will be screened in the uniform blast nursery. So here the best plant that is having the least scoring, having the maximum recovery of the female parent, and harboring the PI9 and PI54 gene will be ultimately released for multi-location or the station trial for the final release of a variety. So I thank you all for giving me the platform for presenting in this symposium. Thank you.